Okay, welcome to today's video. In the previous video, we looked at the stacking ensemble learning model and considering some base models like the decision tree, random forest, neural network, and then the support vector machine. But in this video, we are going to look at how they are implemented in Python. Okay, yeah. So, and then we will be considering the cross validation and then the hyperparameter tuning in the code. So, let's get right to it.
Okay, so we first import our libraries here. We need the pandas to read our data sets, and then we need a minimum maximum scalar so that it will make sure that our values are within a fixed range. Okay, we also need a train test split so that it will split our data set to test and train data set. Okay, and then we need a grid search CV for our parameter tuning, and then we need a k-fold for our cross validation. Okay, we also need our base models, which is the linear regression, decision tree, random forest, and then the support vector machine here. Okay, since we are dealing with regression problem, we pick the regression aspect of it. Okay, all right. So we also need the multi-layer perceptron, from the neural network. And then we also need some evaluation matrices here, and then since we are using the stacking ensemble learning, we need the stacking regressor or the meta model here. Okay, all right. So here we import our data set using the pandas library. We import our data set, and you can watch the other video if you want to import your data set in Jupyter Notebook. All right, so um, our data. This is our data. Some first 5 rows of our data. We have the year, yield, and then the climate variables here. Okay, so here uh, I I checked whether there is any missing values in my data set, and found that there are some missing values here. So using this code, I took those missing values out. Okay, so you can see that there's no missing values here, right? Alright, so we set our dependent and independent variable. So we say the x is our independent variables, and then y is our dependent variable. So here we drop the year and the yield from our data set. As you can see here, when you drop the year and the yield from our data set, it will be left with the climate variables. So we set the climate variables as our independent variables. Okay, and then here we set the yield as our dependent variable. Okay, so we scale our data set so that we make sure that our values are within range here using this one. And then we split our data set. um so here we say 20% should be for our testing data set, and 80% should be for our training data set. Okay, so after we split our data set, we go on by defining our base models, which are the linear regression, the decision tree, random forest, and then the support vector machine and the neural network. Okay, so this actually defining our base models. So after defining our base models, we go on by defining the hyperparameter tuning, and for the linear regression parameters we don't specify any parameter for it. And then for the decision tree we set um, this these parameters here. So the default one for the maximum depth is none, so we give it a choice with 5, 10, 15, so that it will pick from each of them to get the optimal prediction. Okay, same for the random forest parameters. Set the number of estimators to 100, 200, or 500. The number of estimators is actually the number of decision trees in that random forest. Okay, in that random forest model. Alright, so for the support vector machine, we set DC. DC is actually a regularization parameter. Okay, and the higher the C, the more overfitting the model will be. Okay, and then the lower the C, vice versa. So here I set a lower but not very low C, and then a higher but not very high C. And then for the kernel, I listed these kernels to pick from. So it will just pick a combination of these ones. Okay, that will give us the optimal prediction, right? So for the neural network, we set the number of hidden layers here, and then the activation function we set ReLU, logistic, and then the turn H. You can actually change the activation function. We have sigmoid and the rest, so you can actually change them, but I selected the ReLU, logistic, and then the turn H. Right, so the alpha here that is actually a parameter for the regularization term. Okay, so that is the alpha for the neural networks. We go on by defining the cross validation technique. Okay, so we said we are using the k-fold cross validation. So remember I told you that if you are having a small data set, the best cross validation technique to use will be the k-fold cross validation. Okay, then we said the number of k to be 5. Okay, so I listed some articles in the previous videos who actually used the k to be 5, and it helped in their analysis already. Okay, so and we saw the random state to 42 here. So here we perform the hyperparameter tuning for each of the base models based on negative mean squared error here. So we use the grid search CV here, so that it will find the combination of each of the parameters to get the optimal prediction. Okay, alright, so after performing the hyperparameter tuning here, we fit the the optimal the optimal prediction model for each of the base models. Okay, with our training data set here. Okay, so after training our data set, we use it to predict our test data set here. Okay, so we use all the base models to predict our test data set. When we look at the evaluation performance matrices here, we can see that for the R squared, random forest has the highest R squared, followed by the decision tree. Okay, so we can see that the neural network didn't perform well here. And then when we look at the MAE2, we can see them here. Okay, so these are the performance matrices here. So after performing the performance matrices here, what's the we go on by building the stacking ensemble learning model. Okay, based on those base models here. So we use the stacking regressor, or you can also use the meta model or the meta regressor. We don't have meta regressor though. We have the meta model. If you are dealing with a classification problem, then you will be going for the meta classifier. Then for the mid, so here we use the stacking regressor here. It's actually a linear combination of the base models that will give us the optimal prediction. Okay, so we define our base models here, the optimal prediction for each of the base models here, and then we stack them. Okay, so we fit the stacking ensemble learning model on the training data set here, and then we use it to predict our test data set. So after predicting it, we could see that the R squared for the ensemble learning model is actually okay, and we can see that the R squared for the ensemble learning model is actually lower than the random forest. This is because remember in the previous video I told you that in stacking ensemble learning model, the mistakes made in other models are compensated for by the other models. Okay, so that is why the R squared decreased here. But when you look at the R squared and then the mean squared error, they are actually okay. And actually, an R squared of 0.7 to 1 is actually okay. Okay, all right. So thank you very much.